so now I got the numbers and I have the constants here ready so that we can solve an actual example. So we had the C of ice, of water, and of vapor on our table from the previous class. The C of ice is 2,100 joules per kilogram degree Celsius, C of water is 4,186, and C of vapor is 2,010. These two numbers are very similar, but they're not the same, so make sure you use the correct one. So basically, just to put it in the table, just like the LF and the LV, if you're doing part of an exercise that requires this section of ice, you use the C of ice. So C of ice and the green equation. In this section, you use the C of water. I'm going to put just CW. And if you are in this section, you use the C of vapor in this equation. If you pass through this section, you use LF, and through this section, you use LV. So these are all the constants that you might need to solve a problem. And these are the two equations. So just like the C, the meaning of C, which is specific heat, remember, specific heat is the amount of heat, energy that you need to change the temperature of 1 kilogram of the specific substance by 1 degree Celsius. So that's why the unit is joules per kilogram degree Celsius. It's the energy in joules that you need per 1 kilogram of substance to change 1 degree Celsius. And the latent heat of fusion and vaporization are similar concepts. So the LF is how much energy in joules you need to change phase, the fusion phase, so either from ice to water or from water to ice, of 1 kilogram of water in this case. And the heat of vaporization, 2.26 times 10 to the 6. This is the amount of joules of heat energy that you need to change either from water to vapor or from vapor to water 1 kilogram, so per kilogram of substance that you have. So that's either vapor or water. So let's use these numbers in an example. So we're not going to do thermal equilibrium specifically here. We're going to just use these two equations to determine how much heat we need for something to change from one place in this graph to another place in the graph. So I'm going to solve an example that is, how much heat do you need? So how much heat is needed to convert, let's say, 3 kilograms of ice at negative 20 degrees Celsius to water at, let's say, 35 degrees Celsius. Right, so they're asking us about the heat, the energy. So what we need to solve for, or to determine, is this Q over here. So our initial point is 3 kilograms of ice at negative 20. So that means we're going to start ice at negative 20, we're going to start over here. So this is our starting point, right? And we're going to go to water at 35 degrees Celsius. So water at 35, this is 30, so this is 35. It's somewhere over here. So we're going to go from here through this part of the graph, and a bit of this part of the graph over here. This is what we need to solve, how much heat is needed. So there are 3 sections that we're covering in this problem. We're covering a part of the sea ice, so we're going to need to use this equation with the sea of ice. We're covering this section in which all of the ice needs to turn to water, so we need to use this equation with the LF, because that's the one for ice and water. And we're covering part of this section, so we're going to need to use, again, this equation one extra time with the C of water. So that's this one over here. So our equation for Q, so what we're looking for is our big Q, is going to have 3 different sections, 3 different Qs. So we're going to have 1 Q with ice, 1 Q between ice and water, and a 3rd Q of just water. right? So these are our three equations. If we had gone from here to here, so if I had asked you to vapor at 127 degrees, we would have to do this one, this one, this one, this one, and this one. So that would be 5 sums. So this one with ice, this one with ice and water, this one with water, this one with water and vapor, and this one with vapor. So the maximum amount of Q's that you're going to have is 5. But you can have just 1, you can have 2, you can have 3, you can start here and have 3. Yeah, there's many options, and you're going to explore some of them in the worksheet. But right now, we're just going to do this example of these 3 Q's. So the only thing we need to do is plug in, basically, every number into the equation. So we have our Q. So let's express each one with numbers. So the first one is one of the green ones. Our mass is 3. So we already know that mass is 3. So we have m, c of water, delta t. So I'm going to write it down. So this is m times c of water times delta t of water. So this is, oops, sorry, we're doing ice first. So this is m, c of ice, because we're talking about ice, times the delta T of ice. So right here, we're only going to put the change in temperature that occurred here when it was ice. So in our case, it's from -20 to 0, so it increased 20 degrees. So that's what we're going to put there. So we have mc of ice, delta T of ice. Then our second equation is going to be m times LF. That's the only thing we put in this equation. Perfect. And the third part is going to be with water. So it's the same m times the c of water times the delta T of water. So now we're going to put the change in temperature that happened in this section when we went from 0 to 35. So that's 35 degrees. So let's put our numbers in. So our total Q is going to be, let's see, we have M, which is 3 kilograms. We have CI, which is 2,100. And we have our delta T of ice. So in ice, it went from -20 to 0. That's 0 minus -20, or we can just look at it like this and know that it increased 20 degrees. So we have 20 here, 20 degrees. Perfect, that's one of the terms. The second term is M times L. So again, 3. And we multiply times LF. So 3 times, okay, doesn't fit. So this is times this thing, that's right here. This one, 3.34 times 10 to the 5. That's our second term, that's it. And the third term is for water. So it's the same M of 3. The C of water, which is 4,186, times the delta T of water. So again, in water, it went from 0 to our final temperature of 35. So there was an increase of 35 degrees. So we put here 35. And that's it. So we plug all of this into the calculator, and that's going to give us the answer to the problem. Everything is in joules. Okay, so in the calculator, we put 3 times 2,100 times 20 plus 3 times 3.34 times 10 to the 5 plus 3 times 4,186 times 35. Okay, and that gives me 1,567,530 joules, which is about 1.57 times 10 to the times 10 to the 6 joules. So this is it. This is our answer. Now, what would have happened if instead of asking you to convert from ice at -20 to water at 35, I would have asked you the opposite question. How much heat energy I need to take away from water at 35 degrees to convert it into ice at -20 degrees. So you would have done exactly the same process, but everything would be negative. So the thing here is that when you're going from ice to water and you require energy to do that, you use LF as a positive number, as we did here. When you're going from water to vapor and you require energy, you use LV as the positive number, as we would have done. But if you're going in the opposite direction and you need to take away heat energy from the substance instead of giving it heat energy, you need a negative. So you can put a negative here and a negative here. If instead of going in this direction up the graph, you're going in the opposite direction down the graph. Because the same thing happens if you replicate this graph, but instead of giving energy, you take away energy, you're going to get this exact graph, but backwards, right? So that would have happened here. Instead of having a positive LF, you would have had a negative LF. But what happened with this and this, these two terms? What would happen to those? So if we were going from water at 35 to ice first, this wouldn't have been positive 35. This would have been negative 35. And if we were going from 0 to negative 20, our change in temperature would have been negative 20 instead of positive 20. We decreased 20 degrees. So basically what would happen is that we would add a negative to every term in the equation. And that is the same as adding a negative in the answer. So we would have gotten exactly the same number, but with a negative in front. And that negative just means that we have to take away energy instead of giving it energy. So if the question is how much heat is needed, and you say you need negative this much energy, it's because you're taking away that energy.